Have you ever wondered how an automated machine knows how to count backwards? Well, today we're diving into a fundamental building block of industrial automation that does exactly that, the PLC countdown instruction, or CTD for short. This little piece of logic is the secret sauce behind everything from filling a case of soda to emptying a giant grain silo. So let's get into it. Just picture a busy factory. You've got products flying down conveyor belts, robotic arms packing boxes. It's organized chaos. But how does the system keep track of it all? How does it know when exactly 12 items are in a carton, or when a parts bin has run completely empty? You might think it's some kind of super complex AI, but nope. The answer is actually a beautifully simple and incredibly reliable tool in ladder logic called the countdown instruction. It's basically the digital scorekeeper that makes so much of modern manufacturing tick. All right, so let's pop the hood on this digital scorekeeper. We're going to break down what it is, how it works, and what makes it, well, count. Okay, so here's the official definition. At its heart, a CTD instruction just subtracts 1 from a number. But the real magic is when it does it. It happens on what's called a false to true signal. So what does that mean? In plain English, it means the counter triggers the exact moment a sensor switches from off to on. Not while it's on, not while it's off, but on that single rising edge of the signal. That's what makes the count happen. The process itself is wonderfully straightforward. First, a signal comes in, maybe a sensor spots a bottle on the line. Second, the current count, which we call the accumulator, drops by 1. And third, the PLC immediately asks itself a question. Have we hit our target number yet? This simple 3-step loop is the engine that drives the whole thing. To really get this, you just need to know its 3 essential parts. First, you've got the accumulator, or .acc. Think of this as the live score, the number that's always changing. And here's a crucial detail. This value is persistent. That means the PLC remembers the count even if the power goes out. Next up is the preset, or .pre. That's your finish line. It's the target number you're counting down to. And finally, and maybe most importantly, you have the done bit, or .dn. This is just a simple flag, an on-off switch, that flips to on the second your accumulator hits the preset. And this is the whole point. The done bit is the trigger for action. See, the countdown itself doesn't really do anything on its own. It's the done bit flipping on that tells the rest of the program, okay, time for the next step. That signal can be used to stop a motor, activate a piston, sound an alarm, you name it. The count is just the setup. The done bit is the payoff. Now, you can't really talk about counting down without mentioning its other half, counting up. So let's do a quick side-by-side comparison. This is going to put the CTD's unique job into perfect focus. It's a classic case of opposites, really. The count up, or CTU, adds 1. The CTD, as we know, subtracts 1. Their done conditions are perfect mirror images, too. A CTU is done when its accumulator is greater than or equal to the preset, perfect for counting how many parts you've made. A CTD is done when its accumulator is less than or equal to the preset, which is ideal for tracking how many parts are left. But here's where it gets really cool. These two aren't rivals, they're partners. A really common and powerful technique is to have a CTU and a CTD instruction point to the exact same memory address. When you do that, you create a bidirectional counter. One input adds to the total and another input subtracts from it. This is the foundation for almost any inventory management logic in automation. Okay, enough of the theory. Let's see how this instruction actually gets its hands dirty in the real world. This is where that simple logic really comes to life. Probably the most common job for a CTD is tracking a production batch. Let's imagine our task is to fill boxes with a specific number of widgets. The CTD is absolutely the perfect tool for this. So to kick things off, we load our accumulator with the total batch size. In this case, let's say it's 50. Our preset, the number we're counting down to, will be 0. So right now the system knows we have 50 parts to go. Then a widget comes down the conveyor. A sensor sees it and click, sends that little pulse to the PLC. The CTD instruction gets that signal and immediately decrements the accumulator. Just like that, we're down to 49 parts remaining. This will happen again and again for every single part. Finally, after that 50th and final part is sensed, the accumulator value drops from 1 down to 0. And because our accumulator, which is 0, is now less than or equal to our preset, which is also 0, bam, the done bit instantly turns on. That's the signal to stop this conveyor, move the full box out, and bring an empty one in. This cycle is complete.
Awesome. But before we wrap up, we need to cover a few important technical details and potential errors. These are the gotchas that every programmer absolutely needs to be aware of.
So it's really important to remember that these counters are not infinite. They have hard-coded mathematical limits. On older 16-bit PLC platforms like RSLogix 500, you can count from about -32,000 up to +32,000. But on modern 32-bit systems like Studio 5000, that range explodes to plus or minus 2.1 billion.
Let's focus on that older 16-bit system for a moment. Its absolute lowest possible value is -32,668. Now, you might think you'd never hit that, but on a fast-running machine with a runaway sensor, it's definitely possible.
So that begs the question, what happens if the counter is sitting at its absolute minimum value, and it gets one more signal to count down? The number can't go any lower, so where does it go? Does the whole thing just crash? Well, no, because the PLC has a built-in safety net for this exact situation. It's a diagnostic flag called the Underflow bit, or .un. If the counter tries to go below its minimum limit, two things happen. First, that .un bit turns on, warning the programmer there's a problem. And second, the accumulator value rolls over all the way to its maximum positive value. It's like the odometer on an old car flipping over. And just to complete the picture, while our CTD has an underflow bit for going too low, its counterpart, the CTU, has an overflow bit, the .ov bit, for going too high. It's really that simple. Overflow is for counting up, past the max limit, and underflow is for counting down past the min limit, two sides of the exact same coin.
All right, let's wrap this all up with the key takeaways. Number 1, the CTD instruction subtracts 1 from a counter. 2, the done bit kicks on when the count is less than or equal to your target. 3, it's perfect for tracking anything that's running out, like inventory. 4, it's the polar opposite of the count up instruction. And finally, 5, always watch out for the underflow bit to avoid any weird counting errors.
And that is the countdown instruction in a nutshell. It's a simple, elegant, and really powerful tool for controlling all kinds of automated processes. It's a fantastic reminder that sometimes the most complex operations are built on the simplest and most logical ideas. So that leaves me with one question for you. Now that you have this piece of the puzzle, what's the first process you would want to automate?